sum of numbers with unit digit k. Let's start with the problem. We are given two inputs, which is two integers, num and k. We consider set of positive integers with the following properties. So only positive integers. Unit digits of each integer is k, and unit digit is actually basically the last digit of the integer. That's what's called as the unit digit here, and that is represented by the variable k. And then the sum of the integer that we are targeting is called num. So this is the target of sum of all the integers. So we are asked to return the minimum possible size of such a set of integers, or -1 if no such exists. So we are looking for the minimum number of a set, minimum number of a size of set that when we sum all the member in that set, it should result in the num. Okay, so the set, here is some notes that the set can actually be multiple instances of the same integer. So let's say we have k9, we can have all set equal to 9. And the sum of an empty set is considered 0. It means that empty set is considered as an answer. Choosing nothing is considered as a good answer if it fulfills the value. It means this is a edge case where when num is 0, we can always solve it. It is trivially solved because returning a set of nothing will answer it. The units digit, this is what I mentioned just now, is the rightmost digit of the number. So let's go with an example. When num is 58, k is 9, there is the minimum size of the set to fulfill those conditions is 2. An example of the set is 9 and 49, right? 9 and 49 both has the last digit of 9, so that fulfills the k equal to 9. And then when we sum it, 9 plus 49, it is 58. That fulfills the target sum, 58. And then it can be proved that there is nothing possible that is less than 1, less than 2. 2 is already the minimum number of set. 1939 is also the same. All ended with 9, and when you sum it, it will result in 58. This is another version of the solution of the set that could result in the size of 2. Why size of 1 is impossible? Because this is 58, the last digit is 8. So if we want to have the size of 1, it should be itself. And it's impossible because the last digit is 8, which is not fulfilling the condition that k is 9. The last digit should be 9. So that's about it. 37k equal to 2 is -1 because there is no way that we can create anything out of with the last digit is 2 that will be summed into 37, right? Num 0k is 7. This is possible because remember just now that the empty set is 0. So when we got the question num is 0, the answer is trivial. We just return empty sets. Now all is all, we have this constraint k, maximum is 0 to 9, of course, that's the existing digit in a 10 numbers, right? And then num is between 0 to 3000. Okay, now how to solve this? Okay, first of all, we need to realize the conditions. There is one trivial condition. Trivial when num is 0. We can always return that it is, we return just empty set. So the answer will always be 0, right? Another trivial thing is when num is 1, which is that the last digit of the num, this should be equal with the k. When that happens, of course, sorry, not num is 1. Last digit equal to number is k, then the answer will of course be 1, right? Um, unless it is 0. And then another thing is, how do, for example, we know this example of num37 equal to and k2 is actually impossible. How? So if we notice that the requirement that the last digit should always be k, it means that we can detect whether something is possible or not by comparing the last digit of the target sum with what is possible to become the last digit when we have a certain k. So if we have k is 2, what are the possible last digit that can be created by number 2? It will be 2, 2 plus 2, 4, 2 times 3, 6, 2 times 4, 8, 2 times 4, 5 is 10. This one becomes last digit 0, right? 2 times 6 is 12, last digit become 2. So if you 2 times 7, 14, last digit become 14. If you see, it is repeated. Once it goes to something, it will be returned. It will be circled back. The last digit can be created by 2 into itself, right? So in this case, we know that the rest of this will just repeat it of this one. So all possible last digit that can be built with k equal to 2 is only 2, 4, 6, 8, 0. 7 is not part of it. So it is impossible for us to actually build a sum of 7 with last digit always 2, because these are the only possible thing when you are restricted to last digit equal to 2. Remember what is this? 1, 2 plus 2, 2 plus 2 plus 2, or basically 2 times 3, then 2 times 4, and etc. So that's how we can generate all possible last digit can be built on top of k equal to 2. And so with another k, we can always build something like this, and it will be repeated at some point. And once we got the set, the unique set, that we know that those are the possible numbers and last digit that can be generated with that restriction of k. Okay, now what else we need to do? So it means that when we can actually, by looking at this uh, fact, we know that we can check whether we can read something by checking all the possible things that can be built with the k. And once that is done, we have the freedom to actually attach whatever it is at the front of the numbers, right? So we once we detect that the last digit is actually okay, it's basically is the solution. But so for example, if we took this one, okay, we took this one. So what are the possible things can be built with k equal to 9? It will be 9. 9 times 2 is 18. 27. And then what else? 9 times 4 is 36. 45. 54. 63. 72. 81. 90. 99. So this one is already a repeated one, right? So once this last digit are repeated, which is this, we don't need to go further. So these are all the unique last digit that can be built with k equal to 9. Now, how about 58? 58 is 8, and we have 8 as the last digit. Let me clean this up into only the last digit, okay? So now we know that 8 is this. So, and this was 9 times 2. So the answer is 2, right? And it's correct. The answer is 2. So that's how it is. Because why 2? Because 8, the last digit 8 is built with 9 times 2. It means that we need 2 9. And because we have the freedom to build anything above the 9, it means we already solved it. We only need 2. We only need 2 with something that always ended the digit with 9. So for example, this can be 49. This can be this one. This also can be this one, right? So you can see that the rest of the digit is an easy stuff. Once you already check that the last digit is possible, you already get the answer. 8 coming from 9 times 2. So the answer is 2. Okay, so this is a happy case, happy normal case. Let's see what is something that we need to take care, to be careful about. So how about 8? This should be answered as negative 1, right? But if we just use the logic we do now, we will meet that the 8 here is possible. So we need to check here actually. So what we need to store is we need to check here actually the digit 8 is coming from multipliers of 2, right? It means we need to check 9 times 2 that the num should be greater than 9 times 2. If num is less than 9 times 2, it means it's impossible because the minimum value that can be generated with the last digit 8 and k is 9 is 18. So we need to check this to ensure that it is possible at all. Otherwise, when this is less than this, it means it's impossible to build. And when it's impossible to build, we have negative 1. So this is the condition we need to check. And that's about it, about the tactic and so on. To summarize, we got to know the core idea of the tactic, in essence, is the fact of the last digit. That when we have a certain restriction, the last digit is something like k, we know that there is only a limited set of possible last digit for the target sum. And we use that to build our algorithm to find this minimum size of set. That's about the tactic. Let's implement it. Okay. The code implementation, let's start with the trivial first. So if num is 0, we will return 0. Okay. And then last digit of num is, we can do it easily with modulus 10. And then if last digit of num is the same with k, it is also trivially easy. The answer is sorry, this is not last digit of num, it's num equal to k. Is num equal to k, it is trivially easy that it will be returning 1, right? Because it's the same thing. Of course, it will be 1. If it is 0, we already cater it first. And then, all is all. Now we start with the unit thing. So first, we need to have possible last digits, which is this kind of things based on the k. Okay, let's have it like this. And then what we need to do is as simple as doing the loop from 1 to 10, 11. Why 1 to 11? Because if you notice, whatever the number is, it will have a repeated pattern after 10 digits. Why 10? Because this is 10 numbers, 10 multipliers of numbers. Uh, so what we need to do is last digit become the what you call it k times I, and then we modulo it with 10. Basically, I'm doing multiplication, then I modulo it. Okay. If last digit in possible last digit already, what do? We break because we already make the repetition. Because it's not always that you need to get into 10 to actually get a repeated number. For example, like 2, you only 1, 2, 3, 4, 5, and you already get a repeated one at the 6th point. So you can always break early, but you cannot get worse than 10. And then after that, if last digit impossible last digit, we break. Otherwise, we make the entry here. And what is the value here? The value here will be the I. Why the I? Because that will be the answers, right? And then after this is all said and done, we just need to check what is the last digit of num. Last digit of num is this. And then we need to check if what you call it, last digit num not in possible last digits. This means this is impossible, right? Now if it is in the last possible last digit, we need to check this one, right? So potential answer is possible last digits of the last digit num. Okay, but we need to check if num is less than potential answer times k. We know it means it's impossible. Otherwise, we return the potential answer. Okay, so that's about it. Let's try. Why slow? Okay, it's showing answer 2 and then it's correct. Let's try what? 8, 9, whether it's showing -1. 8, 9. It's pretty slow. Though it is illogical to be slow if we look at the big O, if we think about the big O, which we'll talk about later. But let's try to submit this first, whether it is accepted. It could be that the LeetCode server today is just slow rather than the algorithm we write is slow. It's accepted, so it's performant enough. And let's see about the time complexity. The time complexity, this one is big O1, just comparison. This one is big O11, so you can call this big O1, big O11, right? This is just checking, entry, assignment. Yeah, just big O11, another big O1. This is just big O1, possible last digit big O1. This is just big O1, just checking. So in total, this is just big O1. The biggest one is big O11, so it's just a big O1. So that's about it. Yeah, there is nothing about the size here that can make this actually harder than something of a bigger size. So the time complexity for this with this kind of logic is just big O1. It's pretty fast. Though I don't know why today I think LeetCode server is pretty slow. So thank you for watching.